Okay, welcome back, everybody. So, um, the end of yesterday's lecture, we were attempting to write in as convenient a form as possible um, a solution to Laplace's equation, or the Dirichlet problem for Laplace's equation on a disk. So, what does that look like? Just remember from yesterday, the idea is or I am seeking a solution to Laplace's equation, so something whose Laplacian is 0 on the interior of this disk. And on the boundary of this disk, I have some prescribed value of the function, right? So the function u that I seek has this prescribed functional value h, so h is some function defined on this boundary here, right? And so we spoke about this when we first mentioned Laplace's equation, that the Dirichlet problem amounts to finding like a harmonic function, right, that has the prescribed boundary condition, right, that is equal to some given function h on this boundary. So in this case, the domain in question is open disk. Its boundary is this circle, okay, of radius a in this case. All right, and so our idea was to switch to polar coordinates. In polar coordinates, you can work out that the Laplacian with respect to polar coordinates is given by this expression. Okay, if u is equal to some h on this boundary, well, this boundary set can be written really easily as just the set of polar coordinates points where r is equal to a, right? So u is equal to a function of a single variable theta, right, when we've switched to polar coordinates. This is useful because, of course, if u is a function of x and y, h is also a function of x and y here on this boundary, but since we're using polar coordinates and this boundary is just the set r equals a, this has to be a function purely of theta, okay, on this boundary. And we used our separation of variables, right? We used our separation of variables algorithm here. Once we had translated this original equation, this Dirichlet problem for Laplace's equation on the disk, using change of variables, here's what the Laplacian of u looks like. And so rewriting this PDE, the PDE that I want to solve in polar coordinates is this thing, right? So there it is. So I seek a solution that satisfies this equation on the interior of the disk and then the boundary condition on the boundary of the disk. So using separation of variables now to separate my variables r and theta yields two eigenvalue problems. The first one this is more complicated than I'm used to, right? But this one is exactly an eigenvalue problem that I'm used to. Now, the issue here was that these boundary conditions did not lend themselves seemingly as easily as the boundary conditions in the previous eigenvalue problems, right? So in the previous way that we've done separation of variables, we had boundary conditions, and because we were in one spatial dimension, this led to boundary conditions for the eigenvalue problems that were on our list, right? So Dirichlet, Neumann, periodic, or mixed boundary conditions. We even did an example of Robin boundary conditions, right, where we had to approximate the eigenvalues. So, but in this case, this is now we have this more complicated boundary condition, but the switch to polar coordinates actually imposes some implicit boundary conditions here, which are periodic boundary conditions. And periodic boundary conditions were on our list, right? In fact, directly from that, what was the solution to this? So we solved this eigenvalue problem first to find lambda, and then we will later put that same lambda over here to solve this eigenvalue problem. So doing that, solving this eigenvalue problem, led us to find that the eigenvalues in this case were n squared, right? We're in 0, 1, 2, so 0 is an eigenvalue here. And the eigenfunctions are given by this linear combination of sines and cosines. We know that, going back to this eigenvalue problem, the solution that we got in this case for periodic boundary conditions was the full Fourier series, right? It was the eigenfunctions associated with the full Fourier series, right? So yes, both cosines and sines showing up here. When n is equal to 0, this leads to just a constant eigenfunction, theta naught. Okay, so now that we found these eigenvalues, we plug that into our other eigenvalue problem to find the R eigenfunctions. Okay, so we found the theta eigenfunctions. We plug lambda sub n equals n squared into the previous eigenvalue problem. We get this eigenvalue problem. Now, this on its face looks like this is a variable coefficients ODE, right? The variable on R, remember, separation of variables. The variable we're using for R is little r here, right? And little r shows up as coefficient functions in this ODE. So this is an example of variable coefficient ODE, right? That's typically something that when you dealt with it in your ODE class, you were either given the fundamental solutions for it, right? You were either given a fundamental solution set, or it was a very special case, you were told how you could construct it. In this case, this is a very, very special type of ODE called a Cauchy-Euler ODE, where the exponent on first of all, it's polynomial, but it's even more special than that. The exponent on R here is the same as the order of the derivative on the big R term, right? And so, of course, you might be able to just have guessed this anyway, but the form of the solution to this type of ODE you should seek is of this form. It's R to some exponent. Okay, and so plugging that into our equation yielded that actually this exponent had to be plus or minus n. That was the only option here. And so second order ODE, so I get two linearly independent fundamental solutions indicated by this. But we wanted to rule out this most general form here. And the way that we ruled out this most general form is we considered what this thing should look like. Right? Again, we are seeking something that satisfies this everywhere on the interior. I don't want a function that has a singularity. So you may recall that when we did this, right, when we talked about this previously, we talked about fundamental solutions to Laplace's equation, but those fundamental solutions blew up at the origin. Right? So they weren't even continuous at the origin, let alone C2. But I want this to be satisfied everywhere on the disk. So I don't want this to blow up even at a single point. I actually want it to be C2 everywhere so that this expression is meaningful everywhere on the interior of this disk. And so I want to disinclude, right? I want to exclude solutions like this that would blow up at the origin, which is r equals 0. Well, if d sub n is taken to be anything other than identically 0, then this term, right, this term is gonna cause this to blow up, right? So if r is equal to 0 here, this is going to blow up. If we look at the n equals 0 case where I would get a log out of this, it would also blow up at 0. So I need to take d sub n equals 0 for every choice of n. Right, 0, 1, 2, 3, 4, and so on. Okay, so every choice of n, this d sub n is 0, so that my eigenfunctions for r look like this. They're r to the n. Okay, now this means that my separated solutions are of this form, which means my completely generic solution consists of a linear combination of these separated products of eigensolutions. So it looks like this, where these coefficients, right, these coefficients result by imposing this boundary condition, but now this h is a function just of theta, and so in terms of this h can be computed, right, as what? These are like the full Fourier coefficients for h as a function of theta, right? That's what this is, where for the a sub n's, n equals 0, 1, 2, 3, 4, 5, 6, and so on here, and for the b sub n's, n is 1, 2, 3, 4, and so on. Okay, so that I get all of these coefficients. Okay. Now, let's actually try to put these into this formula for u, right? So this is where I am. This is where I stopped yesterday, and I want to put these two into this formula for u to see if I can make this look a little bit nicer. Okay. So u of r theta, right, is equal to what? Well, I'm trying to write it in a way that I'm just directly plugging these things in here for everywhere a and b shows up. And so you can check that this is 1 over 2 pi times the integral from 0 to 2 pi of h of phi d phi. Okay, plus, so we'll use a dummy variable phi here, since we need to make this make sense, plus sum from n equals 1 to infinity of r to the n over pi a to the n. I can factor this out here, right? So I have these a to the n's floating around in these coefficients for these terms, but I have this r to the n here. So I can combine those. This would be the sum from n equals 1 to infinity of r to the n over pi a to the n times the integral from 0 to 2 pi of h of phi times what? Well, here, this integral is with respect to phi, right, since we're going to be combining it with these theta terms. So I'm going to have cosine, cosine, and sine, sine, except instead of both being theta, one of them is going to be phi in each pair. So this is going to be h of phi times cosine of n theta times cosine of n phi plus sine of n theta times sine of n phi d phi. Okay. Okay. Well, let's use cosine addition formula here. Or cosine difference formula, rather. To rewrite this expression as 1 over 2 pi times the integral from 0 to 2 pi of, I'm going to factor the h of phi out here, so I'm going to write this as 1 plus 2 times the sum from n equals 1 to infinity of r over a to the n cosine of, this is cosine of n times theta minus phi. If you're wondering what direction this goes in, you know it doesn't matter because cosine's even. Right, times all of that times h of phi d phi. And you can just check that this agrees with the previous line here. If I distribute the h, then I get this integral here, right? The integral from 0 to 2 pi of h of phi d phi. Yep. And then by the cosine difference formula, this whole expression is just cosine of n theta minus phi. And so, yeah, this is exactly what I get here. Okay. All right, good. So now we have actually written out the solution in this form, and you might be inclined to stop here and say, hey, I have my solution as an infinite series, and it incorporates the boundary condition. And so maybe I stop here and switch back to my, my original rectangular coordinates and be done here. But I can go further here because this is substantially nicer than it looks. And the reason this is substantially nicer than it looks, you might say, why would you not just leave it like this? Why would you put it in this form? Because it turns out that this term here is a geometric series. Now, it doesn't look like that at first, okay? So I want to use two facts here, right? So recall two facts. So recall two facts. One, that I can formulate cosine of a complex number in terms of complex exponentials. In fact, if you like, this, you could say this motivates the hyperbolic cosine, or you could say it the other way around, right? So cosine of z is e to the iz plus e to the minus iz over 2. So this, you learn this in complex analysis. You may have seen this otherwise. If you took Math 246 at UMD and you learned the key identities method for dealing with inhomogeneous constant coefficient equations, then this was part of that analysis. This was one of the reasons why eventually your solutions would always have would always be real. Basically, this and the sign identity, those things taken together, taking real and imaginary parts, all of that stuff worked out. So, secondly, recall that for a geometric series, first of all, what is a geometric series? A geometric series is one that looks like this. So say sum, and we'll do the general thing. We'll start it at m. So sum from k equals m to infinity of, say, like I'll write it as big A, r to the k. This is big A times r to the m over 1 minus r if r is less than 1. All right, this is my geometric series formula, if you like. The way that you see how this works, you can let a be 1 and say start this at 0. And just formally, you can show that like an infinite polynomial, 1 plus r squared plus r cubed, and so on out to infinity, has an inverse, which is 1 minus r, right? If you multiply it by 1 minus r, you get 1, right? Assuming you can do that infinite multiplication. So you divide through by 1 minus r, and the sum of the basic geometric series from 0 to infinity of just r to the k is 1 over 1 minus r, right? You can get this one, right? If it starts at k equals m, well, you can instead, that polynomial that you're trying to find the inverse of starts with this as its leading term. Doesn't matter, right? So this is the same. This is really the same thing. This is just a generalization of that formula. So here's the geometric series formula, and the fact that I can write cosine in terms of complex exponentials. That's going to make it easier to see that this is in fact geometric. So I want to take this expression here I have for you and use these two facts to make this substantially simpler. So let's do that. Okay, first I want to deal with this geometric series. So 1 plus 2 times the sum from n equals 1 to infinity of r over a to the n cosine of n times theta minus phi. What is this thing? So the first thing I note if this u is going to be defined, what does r have to satisfy? Let's go back to our restatement of the problem in terms of polar coordinates. Oh, r is less than a. Well, if r is less than a, then what is the size of r over a? R over a is less than 1 since r is less than a. So that's the first thing that tells you that the size of that is nice. But what about this? Right? What about this? Okay. Well, let's rewrite this using what I just wrote about complex exponentials. So this 2 multiplied by the 2 in the denominator here cancels out, and I'm left with these complex exponential terms. So rewriting this, this is 1 plus the sum from n equals 1, so this is n equals 1 to infinity, of r over a to the n e to the I n times theta minus phi plus the sum from n equals 1 to infinity of r over a to the n times e to the minus I n theta minus phi. These are both geometric series. R over a is less than 1. We know that, like, what is this, right? E to the iz. What is that expression, right? What are these? Right? These are 1. Okay. And so these terms here, right, satisfy their absolute value, or their modulus, are both less than 1. And so I can apply the geometric series formula. Right, just to remind you, here it is. So what is that? This is 1 plus geometric series formula for this sum is r, because this starts at 1 instead of 0, right? So this would be, I'll go ahead and do the algebra and distribute a in the denominator. So this would be re to the I theta minus phi divided by a minus r e to the I theta minus phi. Do you believe me? This was an r over a until I distributed this would be 1 minus r over a e to the I theta minus phi, but the a is distributed in the denominator. 1 times a is a, r over a times a is r. So that's where that comes from. Plus r e to the minus I theta minus phi over a minus r e to the minus I theta minus phi. Okay. Now, let's see. How can I combine these? I want to get a common denominator here. I want to get a common denominator here and add these. When I get a common denominator and add these things, what do I get? Doing a little bit of algebra here, of course, getting common denominator here as well. What do I get? I get, ultimately, to make all of this work out, I'm multiplying this fraction by, a, like a minus r e to the minus I theta minus phi over, so that's my fraction here. The term in the fraction here would be a minus r e to the plus I theta minus phi here. Here I would be multiplying by both. And so doing some algebra here, I get that this is a squared minus r squared in the numerator divided by a squared minus 2ar cosine of theta minus phi plus r squared. Okay, this is my expression that I get. Now you might say, wait, I actually liked it more when it was just an infinite sum. Hold on, it's coming. It will take a second to realize that this allows us to rewrite this in a nice way, but it is coming. And so here was my expression for u, my solution, but I just rewrote this geometric series using this. So putting this into here, I want to rewrite an expression for u. So u of r theta is equal to what? It's equal to a squared minus r squared over 2 pi times the integral from 0 to 2 pi of h of phi over a squared minus 2ar cosine of theta minus phi plus r squared d phi. Oh, that is a nicer formula, right? In fact, I've written it without an infinite sum, right? You might say, well, isn't an integral kind of an infinite sum? But don't fight me too hard on that, right? We don't have a sum symbol showing up here, so that's what I mean. Okay. So this is nice, but ultimately maybe you're a little bit dissatisfied with what it is that's going on here, because after all, what was I originally asked to solve? Right? Originally, I was asked to solve this equation, right? Clearly in rectangular coordinates, this is how all this was expressed. I changed to polar coordinates to make my life easier, right, to do this separation of variables problem. But I didn't, now I have an answer in terms of those polar coordinates. That's fine. But what about switching back to rectangular coordinates? How does this look in rectangular coordinates? So to see that, I'm going to have to do a little bit of geometry here. So let's put this back into rectangular coordinates. Okay. So to do that, let's draw a little picture. Okay, so first, consider the following picture. Okay, so let's say I have my disk. Okay, here is the center of the disk. Okay, here is my vector x, right? My goal is to write my solution at a point, a generic point in the interior of this disk, right? Technically, I'm solving the PDE on the open disk so that this boundary is not even included in that consideration. But this boundary is where my prescribed values are, right? So I'm solving for a solution to my PDE that is a prescribed function on this boundary. Now, let's say that I pick a point, say x prime, on the boundary. I want to draw in a picture here. So first of all, the distance from my center point to the boundary point is the radius of this disk, which is a. The distance from my center point to my generic point in the disk, x, is of course r in the polar coordinates, right? That is literally what r is in polar coordinates. Okay. Well, this angle between x and, say, x prime, right, is what? What is that represented by in this formulation, right? In this formulation, this theta minus phi is exactly this angle between these two. In fact, right, if theta is, if theta is measured from some, we'll just, here, let's draw in another, let's put my disk actually in the plane instead of just kind of disembodied here, right? So here we'll say is the x-axis. This theta is typically measured from the positive x-axis, so we'll say that this whole angle from the positive x-axis to x is theta. The angle from positive x-axis to phi, or sorry, the positive x-axis to x prime, or this radius drawn from the center to x prime is phi. So then this angle between these would be theta minus phi. Okay. So if the point x is associated, why did I do that? So if the point x is associated to the pair r theta, then clearly like this distance from x to the origin is r, and this measurement from the positive x-axis over to this ray that x lies on is theta, right? Okay, so now this whole picture makes sense. But now the question is, what is that distance? Well, I can write that distance as the length of x minus x prime. How can I find out that distance? This distance it's not a hypotenuse because this is not guaranteed to be a right triangle, but it's the side across from this angle, and I know the other two sides. And so, by the law of cosines, right, remember that from high school, by the law of cosines, this side length, which is the length of vector x minus x prime, this side length squared is equal to what? A squared plus 2ar cosine, or sorry, this is a squared minus 2ar cosine of theta minus phi plus r squared. Now you might have remember this written as a squared plus r squared minus this term. I wrote it like this so that you can note, hey, wait, that is exactly the denominator that shows up here. R squared, of course, is the length of x squared. And so, what does this mean? Since our solution is of this form, then how can I switch back to rectangular coordinates? Well, note that if I am, say, going to rewrite this integral in terms of a integral around this curve, you can think about that as a surface integral or a line integral, however you want to think about that. If I do this with respect to this x prime, right, then note that ds sub x is a d phi. Right, that is the switch here, right? And so how does this means I'm going to, so the only thing going between this variable and a variable taking me around this circular boundary is a, this factor of a. Of course, if we were doing this on unit disk, these would be equal. Okay, that means I'm going to have to divide by a in my formula. So I'm going to have a 2 pi a showing up in the denominator here. And so what do I get here? This is u of x, which is the thing that I sought, right? U at a point xy is given by a squared minus r is the length of the vector x. So this is the length of x squared over 2 pi a times the integral over the boundary of the disk of radius a, which we'll write as centered at the origin. So this is the integral over that boundary, over that circular boundary, centered at 0 of radius a, of h of x prime over the length of x minus x prime, the distance from x to x prime squared, ds sub x prime. This is the variable here. Okay. And so what is this? Right? This is now my solution to the original problem on this disk of radius a. This is my solution to what if I want to seek a function whose Laplacian is 0 on the open disk of radius a with prescribed values given by the function h on the boundary. It comes from this formula. Now, a couple of things. So first, this is called Poisson's formula. So this is called Poisson's formula. Okay, so this is, I want to note a couple of things here. One, note that when we were talking kind of conceptually about what we might expect out of the behavior of a solution like this, notice that this expression is some kind of expression involving in some way an average, right, taken over the boundary, right? How is this an average over the boundary? I have an integral over this boundary circle, and that integral over that boundary circle is an integral of something here. I'll talk about that in a second. The thing I'm dividing by outside, this 2 pi a, what is that? That is the circumference of this circle. That is actually the distance around this circle, or the length of that boundary, right? And I'm dividing by that here. So it is this kind of averaging thing, and it has all those same kind of properties we called this infinite propagation speed, right? Where to know the value of the solution at any point in the interior of the disk meant that we had to integrate over the entire boundary, right? So values on the boundary were like instantly apparent, right, in at the different points in the disk, right? And so every point was some kind of like averaging thing. And remember, one of the key things that these harmonic functions satisfy is what's called the mean value property, which is that they are equal in some sense to like an average, a mean value over the region in question. Okay, so they satisfy that property. So that is just directly apparent from Poisson's formula. The other thing, you might say, can I think of this as convolution? And the answer is yes, in a way. In fact, this is done. So this Poisson's formula can be derived without separation of variables. Okay, in the text, this is derived in chapter 8. Is it chapter 8 and 10, I should say? Chapter 8 and 10 using Green's formula, or Green's functions, I should say. Green's functions and the fundamental solutions to Laplace's equation. And so what does this mean? So Green's functions we didn't really talk about. I think I just barely mentioned them. Fundamental solutions to Laplace's equations. Recall that the fundamental solutions to Laplace's equation, you might remember, look like they have the following form. Let me look these up for you real quick. So this is just so you can see them on screen without me having to rewrite them. Let's see. Yeah, here we go. These were the fundamental solutions. Okay, we're in dimension 2 here, so it should be something like this. Is that ultimately something I end up getting here? Like, where does that come into this picture? Well, it's a little complicated to say, but let's at least flash kind of the idea here on the screen, just so you can see this. So let me find probably the most. Yeah, here we go. So there is a definition. This is from chapter 10 of what a Green's function is. There it is. I'm not going to go too much into this, but notice that the Green's function is defined in terms of these fundamental solutions to Laplace's equation plus this extra term here. Okay. And so you might see that that extra term, I went away before I showed you, the extra term satisfies this boundary condition. This is so that all of this stuff works. And then the actual solution is, this is in the n equals 3 case, which you don't have to worry about. You can specialize to the 2D case, and this works perfectly fine. Let's look at the following. So what happens when I try to compute the Green's function for the ball? So here's the problem. Here's the ball. The boundary, of course, is the sphere if we're thinking of this in R3. Then the resulting Green's function that is found looks like this. Okay. So that's a little different. And then ultimately, when I find solution, this is what I get. Where now this is an integral over the boundary sphere. So this is what the expression looks like one dimension up. Notice where g is the boundary condition function. Let's go back to our problem. There it is. Okay, again, this is in n equals 3. Don't worry about that. Focus on the actual form the thing takes. Here, look at this. Now this 4 pi a is what? What is that? Well, look at how similar this is to our formula here to convince yourself that, oh, this sort of thing is actually, we did it using separation of variables to get us here so that we didn't have to go through all the Green's function stuff. Okay, but actually this form is how the solution looks not just on a 2D ball, right, which is a disk, right? So not just on a disk, but also an n-dimensional ball. This formula can be generalized where the constants involved change slightly to make this work, but this formula is somehow basically the prototypical formula for the rest of these dimensions here. But we did this, explicitly using a lot of algebra, geometry, and separation of variables specifically. Okay. All right. And so that is that. Now, that is probably one of the best applications of this stuff because this is a very important formula associated with Laplace's equation. You might complain and say, well, we only really solved Laplace's equation on the rectangle and on the disk. So what about on a generic domain? We're not going to go down that path, but this does open up the door to doing this in higher dimensions. So this, our study of Laplace's equation, maybe leads us to consider, now that we've kind of got it under our belt, that, oh, higher spatial dimensions, like I can deal with them in some way. But this leads us to consider higher dimensional, so 2D for now, heat and wave equations. Okay. And so, what is kind of the overarching picture going forward, right? So, long-term goal. This method of separation of variables really depends on this expanding, I should say, this expanding in eigenfunctions corresponding to some, we'll say, compact symmetric differential operator, right, on a Hilbert space. Okay, you don't have to worry about what a Hilbert space is, but that's ultimately what's going on here. So expanding in eigenfunctions corresponding to some compact symmetric operator on a Hilbert space, this is taken care of by what's called the spectral theorem for a compact symmetric operator on a Hilbert space. Now, the reason I'm throwing all of these words at you is not because it matters whether or not we go through and define every single one of these terms. We don't have time to do that. But this is merely to show you what it is that awaits you if you keep going down this path. Ultimately, all of this stuff comes back to this, right? The operator in question that we considered, this compact symmetric operator in question, was this thing. I think we called it script A, right? So in our analysis of these eigenvalue problems, right, that is the operator in question. It turns out that this theory will apply to operators that are more advanced than this, more complicated than this. In fact, this applies to the operator. Maybe we'll call it L, which is minus the Laplacian. What might such a problem look like, right? What might such an associated eigenvalue problem look like? Well, maybe it looks like this. This would be the Dirichlet problem. Okay. And so, rather than having an eigenvalue problem that was like an ODE coming from this operator, right, that led us to, the eigenvalue problem was this instead, and then x equals 0 on the boundary. So if this is on D and this is on boundary of D, here was my eigenvalue problem for A. My Dirichlet eigenvalue problem for minus the Laplacian looks like this instead. And so, but this same idea of expanding in eigenfunctions works for this more complicated eigenvalue problem in an analogous way that it worked for these simpler eigenvalue problems that we use to exploit this separation of variables algorithm. Okay, and so what is the idea here? Well, for this problem, the eigenfunctions in question were what? They were sines and cosines, right? So the eigenfunctions in this problem were sines and cosines. Right? But for this more complicated problem, now the eigenfunctions are more complicated. So for this more complicated eigenvalue problem, the eigenfunctions are more complicated than sine and cosine. Than sines and cosines. Okay, some examples of some of these types of functions, right? So they are special functions. Functions that have names but are not sine and cosine, right? So some examples, one example are what's called Bessel functions. That's one example. Another example are what are called Legendre polynomials. We may get to see some Legendre polynomials. We will definitely get to see Bessel functions. Probably not in today's lecture, but in tomorrow's lecture. Okay. And so, this will, so these Legendre polynomials, we'll talk about some products of these things which lead to what are called spherical harmonics. Which are important in a variety of applications. And so the idea here, right? So these more general eigenvalue problems are examples of what are called, I've already said these words before, but what are called Sturm-Liouville problems. Oh, there's a U here that I missed. So the eigenfunction or the eigenvalue problems that we've seen already are just very special cases of Sturm-Liouville problems. Sturm-Liouville problems. If you look up like a Sturm-Liouville problem on, say, Wikipedia or just somewhere online, you'll see that it's a substantially more general thing, of which ours is a special case. You can even, if you look up that formula, you can probably see what you need to set to be equal to what in order to get the eigenvalue problems that we're familiar with. Okay. All right. And so, in these cases, these special functions are going to satisfy orthogonality just like our sines and cosines did. And just like our sines and cosines did, they're going to form a basis for the space of reasonable functions that we're investigating in the best cases. And so, these are truly going to be like an analog of the sines and cosines for these more general eigenvalue problems. Okay. All right, but for now, let's do a higher dimensional heat equation. Okay, so for now, let's see how separation of variables applies to the 2D diffusion equation. And let's do this on a rectangle. What does the 2D diffusion equation look like on a rectangle? So here's my example, 2D diffusion equation on rectangle. Let's let our rectangle be like last time. We'll let it be 0 to A cross 0 to B, so its bottom left corner is at the origin. What does this thing look like? Let's prescribe homogeneous Dirichlet boundary conditions here to make this easier. So we'll say this is homogeneous Dirichlet. And so here, this is u sub t is equal to alpha times Laplacian of u, which is uxx plus uyy. All right, for xy in R and for t greater than 0. On the boundary, xyt is equal to 0 for xy in the boundary of R, t greater than 0. And then I have an initial condition. Oh, what did I do here? Hold on. I have an initial condition u of xy0 is now a function phi of xy, right, for x and y in R. Okay. And so, I recall 2D diffusion equation is u sub t equals alpha Laplacian of u. And so here's exactly my homogeneous Dirichlet 2D diffusion equation on this rectangle R. Physically, how would you describe this? Right, so here's my xy plane. Right, so what do I have going on here? I could think of this as being a sheet, right? This is now like a metal sheet. And if I'm thinking about this as like heat, this is saying that my initial temperature distribution on the boundary is 0 everywhere, right? So here's R, here's A, here's B. Of course, the boundary is this set, these 4 lines. So of course I could make this problem more complicated by prescribing conditions that are not just 0 everywhere on the boundary, right? But here, let's see how this works when I get boundary conditions that are 0. Okay, what is my idea here? Well, when I've got one tool in my toolbox here, right, for these boundary value problems, then that's the tool I'm going to use regardless, right? And so my one tool is separation of variables. And so what does separation of variables say for a problem like this? I seek a solution. You might say maybe I just separate the space and the time, but how about separate all of them, right? Separate each variable, even if they're space variables, separate those from each other too. So let's seek a solution that is completely separated, right? That is, it is a product x of x, y of y, t of t. All right, pretty straightforward generalization of our process, right? Okay. So now what? I do the exact same thing. I want to plug this into the PDE to get some expression here. So if this is going to satisfy this diffusion equation, what do I have to have here? I'm going to put the t and the space variables on different sides here. So I'm going to have minus t double prime of t over, just as before, I'll put the alpha with the t. So I have minus t double prime over alpha t is equal to minus x double prime over x minus y double prime over y. Okay. And so I have the time variables here, the space variables here. Well, if these two things are equal for all t and for all xy, then what's the first thing I can say? Both of these expressions must be equal to a constant, just like I did before. Okay, so both of them are equal to a constant. But now I want to consider this part separately. So I take this equation and I add y prime over y to both sides, and I get that minus x double prime of x, sorry, let me make sure that's clearly a double prime, is equal to y double prime of y over y of y plus lambda. And now I have something depending only on x, and on the right something depending only on y, because this is just a constant. So this must also be a constant. We'll call this beta. And so I get 3 eigenvalue problems. Sorry, this shouldn't be T. This is the heat equation, right? This is the heat equation. So this T, there should only be this should be a T prime here, right? So not T double prime, just T prime. Okay, so this is going to lead to 3 eigenvalue problems now instead of 2. What are my eigenvalue problems? So 3 eigenvalue problems. So first, I have minus x double prime over x is equal to beta. So multiplying by x and adding this thing over, I get the first eigenvalue problem is x double prime plus beta x is equal to 0. Okay. The second one, I subtract lambda from both sides to get y double prime over y is equal to beta minus lambda. Multiply by y, and I get beta minus lambda times y is equal to y double prime. So y double prime is equal to lambda minus beta y, right? Yeah, that's right. Or y double prime plus lambda minus beta y is equal to 0. So y double prime plus lambda minus beta y is equal to 0. That's my second eigenvalue problem. My eigenvalue problem for t is actually the same as it was in my 1D case. So this is t prime plus alpha lambda t is equal to 0. Those are my 3 eigenvalue problems. Okay. Now, what do my BCs impose? So here, I have u is 0 everywhere on the boundary. Since I'm seeking a separated solution, that's x times y times t, what does this lead to? So BC, u of x, y, t equals 0 on the boundary. What does this imply? It implies that I get initial conditions x or boundary conditions for this eigenvalue problem. X of 0 is 0, but that's also x of a. All right, so that's the BCs I get here. For y, I get the same thing. So y of 0 is equal to 0 is equal to y of b. And then I get none for this t equation, which is exactly how it was in the 1D case. Okay, so now I have 3 eigenvalue problems. Well, this is my favorite Dirichlet, right? Homogeneous Dirichlet eigenvalue problem. Very happy here, right? Because I immediately know that from this I get eigenvalues which are beta sub n, we'll call them. So beta sub n is n squared pi squared over a squared. And that's for n equals 1, 2, and so on. And eigenfunctions, x sub n of x, which are given as sine of n pi x over a. Okay, so very happy here. Now, what do? Well, I do the thing that I always did, right? I have eigenvalues now. I put these eigenvalues into this eigenvalue problem. To get the eigenvalue problem, y double prime plus lambda minus n squared pi squared over a squared times y is equal to 0. And so I am going to be able to solve this with Dirichlet boundary conditions, right? And what do I get? Let me circle this. Maybe let me use a different color. Okay, so here, what do I get? I get eigenvalues that are what? Lambda minus n squared pi squared over a squared is going to be indexed by an m here. So this is going to be equal to, because normally this wouldn't be here, right? I'd say lambda is equal to like m squared plus pi squared over b squared. This is m squared pi squared over b squared. And so my eigenfunctions here are going to be y sub m of y, which are just a sine of m pi y over b. Okay. But you might have noticed that this means that lambda is like double indexed here. In fact, my eigenvalues, lambda, are indexed by both n and m. So this is, adding this to both sides, this is n squared pi squared over a squared plus m squared pi squared over b squared. They're double indexed. Well, looking ahead, right, just kind of thinking, maybe adopting like an algebraist kind of point of view here, right? Looking ahead, you're thinking, well, okay, my solutions to, say, the diffusion equation, right? Boundary value problem for the diffusion equation in 1D is an infinite sum, right? So, and of course, the index of that sum is the index of the eigenvalues, right? Ultimately, is what's going on here, right? Yes, of course, it's the index on those coefficients. Those coefficients are arising from as the Fourier coefficients in all the examples we did, or related to the Fourier coefficients. And so, but ultimately, those are indexed by the eigenvalues, right? Well, here I have an eigenvalue that has double indices, so looking ahead, what is this going to correspond to in the solution formula? This tells me immediately that my solution formula is now going to be like a double sum, right, over n and m. And if you think about it, of course, that makes sense now because I have two spatial variables in addition to my temporal variable, right? Anyway, let's see what this is. Of course, now I take this lambda, and let me use a different color here, and I put it into my eigenvalue problem for t, finally, and I'm able to write out eigenfunctions for t. So I get eigenfunctions, so t eigenfunctions. What are those? Those are indexed by n and m. Okay, and this is e to the minus alpha times lambda n m, which I'll write as n squared pi squared over a squared plus m squared pi squared over b squared t. And so now, for each n and m equal to 1, 2, 3, each of them are indexing exactly the same way. We have separated solution that is u sub n m x y t, which is x sub n of x, y sub m of y, and t sub nm of t. This is, of course, just going back to the previous page. We got sine, and this e thing. So this is sine of n pi x over a times sine of m pi y over b times e to the minus alpha n squared pi squared over a squared plus m squared pi squared over b squared t. And now we seek solution u of x, y, t that is a double sum of these separated solutions. Okay, and ask, so if I wrote this out, I'm just going to plug these in, right? So this is sum from n equals 1 to infinity to, oh, I should write this as here. Of course, this is, I seek a linear combination, okay, on this double sum. So this would be coefficients that have double indices. We'll call them b sub nm. Right, it needs to go there because that's, I seek a solution that's not just a sum of these things, but a generic linear combination of these things. So this is a sum from 1 to infinity, sum from 1 to infinity of b sub nm sine of n pi x over a sine of m pi y over b e to the minus alpha n squared pi squared over a squared plus m squared pi squared over b squared t. Okay, and ask if I can find b sub n m such that the initial condition holds, which is exactly what I've done in all these examples before, i.e., I'm looking for b sub n such that if I define u by this formula, phi of xy must be equal to u of xy0, which is the sum from n equals 1 to infinity, sum from m equals 1 to infinity, b sub n m sine of n pi x over a sine of m pi y over b. So I'm looking for b sub n m that satisfy this. The question is, can I do this? Question. Can I find such b? The answer, again another miracle, yes. In fact, b sub nm can be computed by more orthogonality stuff as 4 over ab times the integral from 0 to a, the integral from 0 to b, of phi of xy sine of n pi x over a sine of m pi y over b dx dy, or dy dx, whatever. Actually, this is dy, so this would be dy dx. Okay. So note here, what we have found is these are like, this is asking whether or not this function phi of xy can be written as a linear combination of these products of sines. It turns out that these products of sines have orthogonality properties and are orthogonal bases in the same way. So it turns out the set of functions sine n pi x over a sine of m pi y over b for n 1 to infinity and m 1 to infinity. That set is or spans reasonable functions phi of xy and has analogous orthogonality relations that lead to exactly this thing. You can see how similar it is to the 1D case. Okay. In fact, you can compute, so just an example of one, you can compute this, the integral from 0 to a, the integral from 0 to b of sine of n1 pi x over a sine of m1 pi y over b times sine of n2 pi x over a times sine of m2 pi y over b dx or dy dx is equal to 0 if the pair n1 m1 is not the same as the pair n2 m2. You can compute this directly if you like. Probably the quickest way to do this is to use one of Green's identities. But this is indeed an orthogonality relation just like we had in the 1D case. And from that, we get the analogous statement of these as a type of Fourier coefficient, now just for a function that has more than one variable. Okay. And so our initial goal was to solve the 2D diffusion equation on a rectangle. We sought separation of variables in the sense that we sought a triple product now, separating all the variables. And ultimately, we found that a solution looks like this. It looks like this double sum of linear combinations of functions in this way, where these coefficients b sub n m are computed from phi by this formula. So in this problem, if I give you a phi, right, you can compute these b sub n m's and then write the solution for that explicit problem. Okay, so that's a good place to stop, I think. Tomorrow we will talk about Bessel functions, some of these other special functions. We're closing in on, what is basically the end of the material, so it's kind of up to us what specific direction we want to go in here. I thought it was a good idea to show you all some of these special functions because they have applications beyond this course, and they have a ton of wide range of applications in all kinds of various sciences. So anyway, we'll do that tomorrow and Friday, and then that will be it. Friday afternoon, you will get your final exam. You'll have plenty of time to finish it and submit it on Friday itself, but I'm giving you over the weekend to do it, at least till Sunday night. And then your grades will be in basically that Monday, because they have to be. So anyway, that is how it's going to go. So I will see you all tomorrow.